Hello, welcome to today's video on theory of structures. We'll be looking at one of the methods we use to calculate slope and deflection. And the method we'll be looking at today is the conjugate beam method. So this method was proposed by Henry Rich in 1863. With the concept that when we are given a beam, we have to draw the conjugate of the beam. The point you have to notice, we have two beams, the original beam and the conjugate beam. And we have the conjugate. We have original support and the conjugate support. These are one of the things you have to change. You have to change the original support to a conjugate support. So we have, this is a pin support. So the conjugate will still be a pin support. Then you have a ruler support. The conjugate still have a ruler support. Then you have a fixed support. The opposite, you have a free end. This is a free end. You will have a free end. This is the original support. You'll be given in the question. Then you have to change it to a free end. Then when you have a support like an overhanging beam, a support at the middle, the support will turn to an internal hinge. It turns to an internal hinge. We have this at the middle, then it will turn out to be an internal hinge. In the original beam, we have the supports at the middle. Then the conjugate will be an internal hinge. We have a ruler support. Then the conjugate will still be a ruler support. We have a fixed beam. The conjugate will be a free end. This is one thing we have to change. And also, you have to draw a bending moment diagram. And when you draw the bending moment diagram, what you just require to do is the bending moment divided by the flexural rigidity, which so this is an example which asks to calculate the deflection and rotation at point B. So the first step, you calculate the support reaction. You take summation of moment at point A goes to 0. With the convention that positive, negative. So we have negative MA plus 100 multiplied by, you have to get the point load of this UDL, then multiplied by this half, that is the centroid, the distance. We have from the length of the span of the beam is 5 meters. Then when you get the point load, and you divide the 5 by 2, multiply the point loads to get the moment. So So when you simplify all this, you will get this as the final answer, the moment reaction at point A. Then summation of forces in the y direction equals to 0. We have the VE. In the convention that this is plus and this is negative, then VE minus 100 5 equals 0. So VA is equal to 500. So we have gotten the support reaction. The second step is to draw the M over EI diagram. So, to draw the M over EI diagram, you have to calculate within yourself. You look at the question you are given and what you're asked to solve. From there, you're able to know where to calculate your bending moment, the point which is efficient enough to the moment diagram. So, looking at this question, I have a point A and a point B, and the question says get the rotation, deflection at point B. So, I will calculate the bending moment at point A, the midpoint, and the free end B. So, at MA we have 1250 millimeter. Then I have to calculate the bending moment at the midpoint. So to calculate the bending moment at the midpoint, you use the bending moment sign convention, which we have in our previous video. I showed how to use the bending moment sign convention. So if you don't understand, you can go back to the video. So, but if you follow up, I believe you understand how that goes. I'm coming from my left to right. So the bending moment at the midpoint will be negative 500 actually multiplied by the midpoint is 2.5. Then minus 100 you arrive at the bending moment at the midpoint is this. So then you should know that the moment at the free end is always equal to 0. So at the moment at B equals to 0. So we have gotten the bending moments at the necessary points. So the next is to draw the M over EI diagram. Okay, we have that the bending moments at A is negative of this, being that in the free body diagram, I assumed that the support reaction moment, MA, is in anti-clockwise direction. And when we calculated for the MA, we have a positive value, saying that the direction is correct, which is a negative moment. Then at the midpoint, we have this, and at the free end, we have this. So, and bending moment, because this is just a sketch, it could not tell us, it couldn't give us enough information on how the diagram will look like. So, for you to use this method efficiently, you have to know when you have a UDL, how does the bending moment diagram look like? When you have a point load, And also when you have a bearing load, how does the bending moment diagram look like? For a UDL, you will have a curve, a quadratic curve, and the curve can be concave and convex at the same time. So we have at point MH to be this. Then at the midpoint, we have this to be this. Then at the free end, you have 0. So we have something like this. The negative indicates that is a negative bending. So the next step is how to apply the concepts of the conjugate beam method. Remember, in the beginning I said we have two types of beam, the original one and the conjugate. And the concept says that you have to change the supports of the original beam to the conjugate of it. And also you have to change the loading to the virtual load. So we have a cantilever beam at this a fixed support at this point, and this is a free end. The fixed supports return to a free end, while that of the free end return to a fixed support. So our new our conjugate beam is this. This is our point A, and this is our point B. So we changed the supports of the original beam to its conjugate. Then the M over I diagram becomes our new loading. So if the moment is a negative value, then the load will point up and go in this direction. Then if it is positive, it will go in the opposite direction. Another concept is that the slope at any point on the conjugate beam is equal to the shear force, and the deflection at any point on the conjugate beam is equal to the bending moment. Then to get the rotation at B is equal to the shear force at point B on the conjugate beam. And to get the shear force, you need to get the force intensity, because this is a varying load. The intensities are not the same, so you have to convert this to like a point load. And for you to get the intensity of this loading, you have to take the area of the shape they are given. So in this particular one, we have a parabola, and to get the load intensity of a parabola, we take the area, and the area is given by 1/3 BH. Then the height is given by this, now what we have here, and the span of the beam, which is the base, is what we have here. When you simplify all this, you have this as your answer. Is to calculate deflection at beam, which is equals to the moment as beam or the conjugate beam. We still use the bending moment sign convention to calculate the moment at this point. So YB equals to, this is pointing upward, so it's going in a clockwise direction at this point. So, and also we need to get the load intensity multiplied by the centroid. this is the area which will give us the load intensity multiplied by the centroid. When you simplify all this, we arrive at our deflection at beam is equals to this.